Okay, on to systems of equations. Very similar to what you had in linear algebra, similar notation as well. A system of n linear equations and m unknowns, x1 through x sub m being the m unknowns, is a system of the following form. So we've got a linear combination of x1 through x sub m with some coefficients set equal to b sub 1. A second equation, linear combination of x1 through x sub m set equal to b sub 2. And similarly, up through an nth equation, a linear combination of x1 through x sub m set equal to b sub n. So, of course, it's called linear equations because they're linear combinations of the unknowns. So what we'll do, and we have introduced these coefficients using double subscripts in the usual way, such that we can take matrix A to be the matrix with the entries, lowercase a sub ij. We'll take matrix B to be the vector from Rn with its entries, its components, being b1, b2 through b sub n. And we'll take X to be a vector from Rm with its entries, its components, x1, x2 through x sub m, so that we can collect together precisely this information in the matrix equation, AX equals B. Technically, A is a matrix. I guess S and B, X and B are vectors of appropriate dimensions. Matrix A is called the coefficient matrix for a given coefficient matrix and a given vector B. A vector X for which this equation is satisfied is called a solution to the system of equations. If a solution exists, the systems of equations is consistent. If it doesn't exist, then the system of equations is inconsistent. All terminology from linear algebra. Of course, what you did in linear algebra was usually solve systems of equations using elementary row operations. Reduce the matrix to a row echelon form, or maybe reduce row echelon form, find unique solutions, find multiple solutions. You can tell when there's no solution, when the system's inconsistent. What we're going to do here is use the rank of the coefficient matrix and the existence of an inverse of the coefficient matrix to look at solutions to systems of equations, and look at in connection with rank, a lot of stuff with column spaces. All right, we made a little comment in section 2. If we'll take A1 through A sub m, as we commonly did, as column vectors, they're the columns of matrix A, and we let X have components, X1 through X sub m, be a vector from Rm, where A is an n by m matrix, as usual. Then if we have A times X, what we get out is a sum from I equals 1 to m of X sub I, the scalar, times A sub I, the column vector. As we've said, AX produces a linear combination of the columns of matrix A with coefficients given by the components of vector X. We said that 2 or 3 times. So you're getting in the equation, or in the computation, matrix A times column vector X, you're getting a linear combination of the columns of A. So saying that there's an X such that AX equals B is equivalent to saying there's a linear combination of the columns of A that equals B. That is equivalent to saying that vector B is in the column space of matrix A. Remember our notation for column space. Okay, let's drag rank into the conversation. System AX equals B is consistent if and only if the rank of a partition matrix, call it an augmented matrix shortly, let's call it augmented matrix now. The rank of the augmented matrix A augmented with vector B equals the rank of A. So here's one. B is in the column space of A, implies the rank of A equals the rank of A augmented with B. So by adding vector B If it's already in the column space of matrix A, we're not, in a sense, we're not contributing anything new. B is a linear combination of the columns of A. So when we look at the dimension of the column space of A, which is what we're looking at, when we look at the rank of A, looking at the rank of A with an additional column thrown in, which is effectively what we have here, doesn't introduce anything new in terms of dimensions, because vector B, if it's in the column space of matrix A, is already a linear combination of matrix A. You think about it in terms of computing pivots, we could explain it in terms of computations of pivots as well. So if B is in the column space, then we get this relationship. If we get this relationship, rank of A augmented with B equals the rank of A, then that means that the dimension of the column space of A augmented with B is the same as the dimension of the column space of A alone. So vector B isn't contributing anything new in terms of dimensions. And so B itself must actually be in the column space of A. B is an element of the column space. So AX equals B, consistent for matrix B, if and only if rank of A augmented with B equals the rank of A, and there's one. In addition, if A is an n by m matrix with n less than or equal to m, and we have the rank of A equals n, okay, so here's what that means. So let's see, it has less than or equal to number of rows because it has columns. So it's possibly wider than it is tall, more columns possibly than there are rows. So by saying the rank of A equals n, that indicates that A is of full row rank. And if we look at the rank of A augmented with B, okay, that's adding another column. There ain't room to add any more pivots, as it were. So that means the rank of A augmented with B must also be n. There's not room for any more pivots. If we've already got, say we take A and reduce it to row echelon form and look at pivots. Alternatively, if we've got full row rank, then I can't, if I don't add rows, I can't increase the row rank by adding columns. And so the rank's going to stay the same. Adding extra columns accomplishes nothing. Adding extra rows could change the row rank. So in this case, the system AX equals B is consistent for any B in Rn, that is, in the case when we have full row rank. And as we said, we're going to call this matrix A augmented with B, the augmented matrix for this system. Technically, it's a partitioned matrix. It's probably the only partition matrix you saw in sophomore linear algebra. Do more linear algebra, maybe you saw other partitions, but you had to see this in linear algebra. Okay, we're working our way to talking about inverses of matrices. When we have square matrices, then if there's a, we're going to, we don't have commutivity, so left inverse and right inverse are going to become an issue we're about to resolve in the event that we have a square matrix. We've already commented about multiplying matrices on the left and on the right and getting the identity. We're about to label them left and right inverses. Okay, so for A, an n by n non-singular matrix, okay, so A is square. For us, for now, non-singular means full rank. So the rank of A is n. For the ith unit vector, E sub I, the standard basis vector from Rn, we get E sub I in the column space of A. Hey, A is full rank, so the dimension of the column space is n. So the column space must actually be Rn. A is full rank. Rank is n. We're looking at n by n matrix. So say the row space is equal to Rn, or the column space is equal to Rn. Square matrices, the books balance nice and evenly like that. So if we take any vector, like one of the standard basis vectors from Rn, you know that's, say, in the column space. That is, Ax equals E sub I has a solution. Being in the column space, as commented above, means there exists a vector x sub I in this case, such that ax sub I equals e sub I. So there is a solution to, if you like, this system of equations, thinking of the vector x sub I as the vector of unknowns. And you can do this for each of the unit vectors for I equals 1 through n. So we're effectively looking at a system of equations where it's a set of a system of equations where we're looking for x1, where ax1 equals the first standard basis vector, x2, where ax2 equals a second standard basis vector. Of course, what we're going to do is put those standard basis vectors in a matrix. It'll be the identity matrix, and then collect together this collection of n systems of equations together all in one and write it as a full-blown matrix equation, replacing x, that bunch of column vectors of unknowns, with a matrix capital X, and these little e sub I column vectors for I equals 1 to n into a matrix that has those e sub i's as its corresponding columns. So we'll create matrix X, also n by n, with the columns x sub I being these solutions from the system of equations upstairs, and matrix I sub n. By the way, its columns are the e sub i's, the standard basis vectors, you know, the ones and all the zeros. Then we can write these n systems of equations as a single matrix equation, ax equals I sub n. Restrict it to one particular column of x and a corresponding particular column of I sub n, and you get a single equation, well, a single system of equations of this form. All right, so let's see, we're getting into this under the assumption that A is non-singular, square non-singular, better yet, square full rank matrix. Okay, so we know the existence of such a matrix X under those conditions. So what we're getting is AX equals, A is n by n, X is n by n, equals I sub n. So in this particular paragraph, at least, all matrices are square. We started with A square. We just saw that X is square. Identity matrices are square. So we've got AX equals I sub n. Hey, so here's something we can multiply A by on the right to produce an appropriate sized identity matrix. So X is called a right inverse of A. Multiply A on the right by X and get the identity matrix. All right, we're going to say, hey, if that happens under these conditions and we get this right inverse, we also can get a left inverse. If A wasn't square, then it's not such a clean story. I can't use the same right inverse as a left inverse if I don't have a square matrix. The products won't even exist. But we see that under the conditions of square matrix of full rank, there exists a right inverse. Okay. We saw in Theorem 3.3.6 that the rank of a product of matrices, in this case, the rank of I sub n, think of I sub n as matrix A times matrix X, is less than or equal to the minimum of the rank of the two constituent matrices in that product. In this case, rank of A and rank of X. All right. Well, the rank of I sub n is n, it's full rank. The rank of A is n, because that's what we hypothesized at the beginning of the note. Okay, so right-hand side, we got n is less than or equal to the minimum of these two. I know A is n. Well, then the rank of X can't be less than n, or we've got an absurdity. We've got n is less than or equal to something that's in fact less than n, so we can't have that. So it must be that the rank of X also equals n. X is an n by n matrix. It wouldn't be meaningful for the rank of X to be larger than n. So we must have that the rank of X is precisely n. By the way, that means X is a full rank matrix as well. Okay, hey, we just saw when we have a full rank matrix, we showed it for matrix A, we can multiply that full rank matrix on the right by some matrix to get the identity. Well, hey, X is a full rank matrix. So we can do that for x. That is, there exists a matrix, let's call it y, that we can multiply x by on the right to get the identity. So there exists a matrix y, also n by n, such that x times y equals the identity. Same argument as above, only replacing matrix A with matrix X. Concern was that this input matrix be square and full rank, X is square and a full rank. So we can make the same argument for matrix X. Okay. Here's what we've got then. Consider the equation matrix A, it's A times the identity. We saw that the identity can be written as X times Y from this previous argument. So we make a substitution there, A times X times Y. Associativity, we get AX times Y, but we saw upstairs that AX is the identity. So we'll replace that with an identity, got the Y, and we draw the conclusion that A equals Y. If A equals Y, we can substitute into this equation and see X times A equals I sub n. So what we've shown is if we have a right inverse of a square matrix of full rank, then that same right inverse is also a left inverse. X times A equals the identity as well. So when you have non-singular square matrices, then if you have a left inverse, you have a right inverse. So we just, let's see, and we've established the existence of the inverse. We've actually just shown that non-singular means invertible for square matrices. Okay, if we have a full rank matrix A that's square, this matrix B that we just saw exist upstairs, it satisfies the condition. Should read B times A equals A times B equals I sub n, is the inverse of matrix A. So there exists a two-sided inverse. We look at non-square matrices and that won't be meaningful. But when we have square matrices of full rank, they have inverses. Inverses on both the left and the right. If we were trying to confirm we had found an inverse, we'd only have to check it on one side, as we saw from the previous argument. If it works on one side, it works on the other side. An interaction in terms of, so our big advancement with all of that was the statement of the definition of the inverse of a matrix, which we know to exist for full rank matrices, the way we've argued it. All right, so let A be an n by n full rank matrix. The claim is the inverse transposed is the transpose of A inverted. Okay, let's go through the proof of that. That's just a little computational proof. All right, and we get first, the rank of A and the rank of A transpose are the same. A transpose is n by n. Since A is full rank, it must be rank n. So A transpose must be rank n as well. And A transpose is a full rank matrix. Theorem 3.3.2 must tell us rank of A equals the rank of A transpose. That's what makes this work. Okay, so let's take A transpose and multiply it by A inverse transpose. And the claim was A inverse transpose is the inverse of A transpose. So what we're trying to show here is we take A transpose and multiply it by this thing and get the identity. This thing must be the inverse of A transpose. This thing, A inverse transpose, must be the inverse of A transpose. So that's the argument we're making. It's a little odd to follow with the transposes and the inverses all over the place. But let's multiply A transpose by A inverse transpose. Hey, a property of transposes says the transpose of a product is the product of the transposes written in the opposite order. So if we take A inverse A and transpose that, we get A transpose first and A inverse transpose second. So that establishes equality between these two. Also got the transpose sort of isolated on the outside. Hey, A inverse times A, that's the identity transposed. Of course, the identity matrix is symmetric and equals its own transpose. So we've shown A transpose times A inverse transpose equals the identity. That is, A right inverse of A transpose is A inverse transpose. We just saw it'll work as a left transpose as well, provided we have a full rank square matrix, and we do. So that establishes relationship between inverses and transposes. I would suspect, I mean, it might not have stuck in your mind, but you probably saw that in linear algebra as well as an exercise at worst. But that's probably a topic from linear algebra. One reason I speculate that is I see the proof was an easy little computation based on properties of transposes. Let me complain about our textbook again. It's kind of my thing. The textbook uses some odd notation. Sometimes Gentle, the textbook author, denotes A transpose inverse or as, which we could also write as A inverse transpose. It denotes it as A negative T. I just don't like that. I'm happy to throw around the extra symbols. That's a muddling together of some really different things. The -1 indicates an inverse. The T indicates something really different. So I just don't like that. I haven't seen it anywhere else either. To make things worse, sometimes Gentle will even denote AB inverse as A divided by B, and B inverse A is B, I don't know, back divided into A, I guess. I've never seen those symbols used that way. I don't like that at all. I won't do any of that stuff. But you see it in the book, beware. That's how it's being used. All right, so claims about left and right inverses. N by M matrix A, where N is less than or equal to M, has a right inverse if and only if A is a full row rank. N by M matrix, where M is less than or equal to N, has a left inverse if and only if matrix A is a full column rank. Notice in both cases, the full was associated with a smaller dimension. N was smaller. We talked about row rank. N is the number of rows. M was smaller. It's the number of columns. And we talked about full column rank. Let's go through proof of that. Okay. Let's establish this in terms of the right inverse. Yeah. The left inverse will be a very similar argument. Okay, so let A be an N by M matrix. N is less than or equal to M. And let A be full row rank. So the rank of A will be the number of rows, which is N. All right, column space of A, V of A as we've denoted it, would be dimension N, because that's what the rank is, dimension of the column space, if you like. So if we take any E sub I, you know, standard basis element, ith unit vector is what our book calls it. The standard basis of Rn, the ith standard basis vector, I prefer to call it. Any of those vectors, they're in Rn. Hey, but the column space of A being dimension N must equal Rn. So every one of these standard basis vectors is in the column space of matrix A. And you probably know where we're going with this, given the previous conversation. So what we're going to do is say, then there's some collection of scalars. Let's call them x sub I, the components of a vector x sub I. So I said ax sub I equals e sub I. This holds for all of those unit vectors, standard basis vectors. So define matrix X to have those x sub i's as its column. Define matrix I sub n to be the matrix with the e sub i's as its columns. And as we saw before, we've got ax equals I sub n. That's merely rewriting this collection of systems of equations as a matrix equation. So we said, and we've shown that if A is of full row rank, then such a matrix X exists. That is, A has a right inverse. All right, subtly different from what we did before. We were talking square matrices in that previous conversation. Now, not necessarily square, but full row rank implies right inverse. And that's half of the first claim. We need to show the other half. If A has a right inverse, then A must be a full rank. All right. If we had this AX equals I sub n, certainly the rank of I sub n is n. It's an identity matrix. It's got n pivots, if you want to think linear algebra wise. For us, it's column space is all of Rn. So its rank is n, no matter how you slice it. Okay. Theorem 3.6 told us that, hey, if you can write that as a product of matrices, then the rank of this matrix will be less than or equal to the minimum of the rank of those two things we multiply together to get the I sub n. So we get n equals rank of I sub n to be less than or equal to the minimum of the rank of A and the rank of X. Let's see, we're still under the hypotheses. Yeah, okay, so we're still under the hypotheses that rank of A equals n. With rank of A equal to n, then as we argued above, the rank of X has to be n as well. And so X has to be a full column rank as well. All right, now we want to establish the relationship AX equals I sub n implies A is a full row rank. Okay, if AX equals I sub n, if this has a solution, or actually this has a solution, treating X as an unknown matrix, AX equals I sub n has a solution X. Only if A has full row rank n, since what we're looking at over here is a matrix of rank n. I sub n has n linearly independent columns. What you're doing when you do this AX thing is getting linear combinations of the columns of matrix A. So it's kind of this argument again. If this has a solution X, then we know when we plug in X sub 1, we're getting out, so we get the first column of X, we're getting out the first column of I sub n. We plug in X sub 2, we're getting out the second column. So this is only going to happen when we take linear combinations of the columns of A and we're producing the basis of I sub n, and so we have to produce the whole space Rn. That is, A has to have full row rank n due to the linear independence of the columns of the identity matrix is how it's said here. So if we have that right inverse, then we must have A to be of full row rank, must be of rank n. So that's the first claim, if and only if A has a right inverse, if and only if A is a full row rank. Let me just caveat out with a similarly, if we look at the claims about column rank and left inverses. So it's a similar type argument in that setting. We could probably throw some transposes at it and get it in terms of transposes also. Okay, back to the notes. We get from this, actually, if n and m are the same, and we can draw both of these conclusions. If n and m are the same, so we got a square matrix, it's of full row rank and full column rank. So it's a non-singular matrix. It's what we call the non-singular matrix. Then we see that there's both a left inverse and a right inverse. We know from above that they're the same thing. So this links together that idea that a square matrix is non-singular if and only if it's invertible. That's what we took probably as a definition of non-singular in linear algebra, not this stuff about rank. I mean, you probably saw the relationship with rank at some later point, but what we're doing here is consistent with the linear algebra. It just came in a different order. All right, I'm going to look at taking a transpose of a matrix and multiplying it by a matrix. And the beauty of that is it gives us a square matrix, and we can talk about inverses. So if A is an n by m matrix, then matrix AA transpose, that's an n by n matrix. When you do the multiplication works and produces a square matrix. If this matrix AA transpose is a full rank, claim is we can find an inverse of it. We know an inverse exists, so AA transpose inverse does exist, and we can express the right inverse of A using A transpose in this thing. Our claim is, under this assumption of full rank AA transpose, that the right inverse of A is given by AA transpose inverse. All we got to do is multiply them together and watch it happen. So we'll take matrix A right here and multiply it by this other stuff here, and of course you get the identity. This is AA transpose and this is AA transpose inverse. So it's a matrix and it's inverse. Of course you get the identity out. So there's a way to express the inverse of a matrix, a right inverse of a matrix A. I have to say right because we didn't assume the original matrix was square, in terms of this AA transpose thing and its inverse. And we can similarly find a left inverse. A transpose A inverse times A transpose, the claim is a left inverse of A. So let's multiply this by A on the left, and it's as easy as the previous one. Here we've got A transpose A inverted, and here we've got A transpose A. Okay, that's a matrix and its inverse. That'll give us the identity of the appropriate dimensions. So there's a way to find left and right inverses of non-square matrices, a little trick that expresses those in terms of inverses of square matrices, provided the inverses exist. You might have software that lets you find inverses of square matrices, but it might not let you find left and right inverses of non-square matrices. Well, here's a little protocol by which you could find one-sided inverses if you know how to find inverses of square matrices only. Okay, one of the proofs we did above, we saw something similar to the following ideas. Matrices A and B of the same size that have the same rank are called equivalent, denoted A is equivalent to B. So same size and same rank is what we're defining as an equivalence. You in the past probably used this equivalent symbol to indicate row equivalence. Now we might extend it to column equivalence or row and column equivalence. That's part of where we're going with this. So that seems like an odd thing to say, but hopefully the pieces will fall into place when we go through the following arguments. For n by n matrix A with rank R, so rank would be between 0 and the smaller of the two dimensions. If you think pivots, that's all there's room for. The equivalent canonical form of A is the n by m matrix that consists of this partition matrix where we've got an identity, an R by R identity in the upper left, where R was the rank of matrix A, and it's surrounded by all these zeros. Okay, so here's what's going on. If A and B have the same size and the same rank, they're both row equivalent to this thing. So this is kind of a equivalent canonical form of A. It's sort of a representative of the equivalence class that contains A and contains B for that matter. But to tie together, the word equivalent is introduced here with the word row equivalent as you dealt with it in linear algebra. It's the same thing. A is row equivalent to this. B is row equivalent to this as well. And A and B are row equivalent to each other because it's an equivalence relation, reflexive symmetric transitive. All right, if A is an n by m matrix of rank R, then claim is there's matrices P and Q, both products of elementary matrices, such that P times A times Q is the equivalent canonical form of A. That is, P times A times Q equals this thing we just described. All right. If you believe me about the row equivalent stuff, this ain't surprising. Think what happens. Elementary matrices, forget the Q for a second. Look at the PA. All right. So we've taken matrix A and multiplied it on the left by a product of elementary matrices. What do those elementary matrices do to matrix A? They do row operations. Whatever the row operation corresponding to the elementary matrices is, that's what's done to matrix A. So we're doing some row equivalence stuff there. How about the other side? Product of elementary matrices, you're doing column operations there. So what you're doing to A is some row operations reflected by this matrix P, some column operations reflected by this matrix Q, and you've done those things in such a way to take matrix A and change it into this canonical form, equivalent canonical form of matrix A, as we called it. So that's the claim. That's what it means. We've used both row and column operations. That's how the proof will go. Let's look at a proof of that one. Okay, so this is going to be a little clunky, but if you think row reduction, we're just trying to do kind of like a row reduction thing. We've talked about elementary row operations. We haven't defined row echelon form or reduced row echelon form yet. We will shortly, but keep that in mind. That's what is being done in the proof. All right, so what we're trying to do here is take matrix A and do some stuff to its rows and columns to produce, we got a little identity matrix up here. So we got ones along the diagonal from the 1, 1 entry to the RR entry. We got zeros everywhere else. That sounds a lot like some row reduction stuff. Okay, so we're going to prove this by induction. First, the rank of A is greater than 0, so one of its entries is non-zero. The only time we get rank is 0 is when we get the 0 matrix. So there's some non-zero entry out there, call it A sub ij. We're going to do some interchanging of rows and columns to get this thing in the desired form. All right, so what we're going to do is take this ij entry, interchange row 1 and row I. All right, so we're trying to move that ij entry into the 1, 1 position, trying to get it up here in the upper left-hand corner. Interchange row I and row 1 and row I. So we're swapping rows. So we brought this up to the first row, but it's still in the jth column. And then interchange column I and column, column 1 and column J. So we've taken the A sub ij, moved it up to the first row, and then moved it over to the first column in 2 steps. One of those is a row operation. One of them is a column operation. I think I said A is row equivalent to this a while ago. That's incorrect. A is row equivalent to something kind of like this. I might not be able to get, with only row operations, I might not be able to get these, basically these pivots all the way over to the left. I do need column operations on that. So when we talk equivalence, we'll talk row and column operations. I take it back. Both the row and column operations are necessary. It's certainly necessary in the proof. So I'm going to denote that as E sub 1I. We got that elementary matrix on the left. So that's interchanging row 1 and row I. And on the right, E sub 1J super C, using superscripts as C to indicate it's a column operation. And the fact that it's on the right would indicate that you've dealt with a column operation. I think I want to stick those C's in there anyhow, though. And we interchange column 1 and column J. So that gets this ij entry up there in the 1, 1 entry. All right, we want an identity there. Okay, so next, let's take that ij entry that's up there in the 1, 1 position now and divide it by itself. So let's take the first row and divide it by whatever A sub ij is. It ain't 0, right? We found a non-zero entry. We're not dividing by 0. All right, divide the first row by A sub ij. That'll give you a 1 in the 1, 1 position. So we're getting there. So we move things around and scale things to get a 1 in the 1, 1 position. Denote this as E sub 1 over A sub ij times 1. You're taking row 1 and multiplying it by this constant. This is consistent with the E sub SP notation I had in the past. It's a little more awkward because I've got specific numbers this time. And my scalars are a bit more involved, but it's the same notation, really. All right, so we move things around. Now we're scaling that first row. You got a 1 in the 1, 1 position. Any bright ideas now? Yeah, just like you would in linear algebra, let's use that 1 to eliminate everything below it, like you would if you were putting this matrix in row echelon form. And let's use that 1 to eliminate everything to the right of it. So that'll be column operations. So we're going to do row operations to eliminate things below the 1 and column operations to eliminate things to the right of the 1. Okay, so we'll eliminate entries. We'll do our thing and change them to zeros. So we'll take row K, and from row K, we'll subtract the first entry. I'm denoting as B, this revised matrix. So the first entry in row K would be B sub K1, kth row, first entry. Take row K and subtract from it B sub K1 times row 1. All right, that's the manipulations you would do to eliminate that first entry. Remember, in row 1, the first entry is a 1. So you ultimately get in that first entry, you get B sub K1 minus B sub K1. So you get 0 in the first entry, and a bunch of arithmetic happens throughout. So do those row operations, do it for the second row through the last row. So that'll get you all 1s below that 1, 1 entry. I want to call it a pivot because it is a pivot. And let's see. That'll produce, let's call it matrix C. Here are the corresponding elementary matrices. Remember, I'm trying to take matrix A and surround it with elementary matrices. So here's where we are so far. We've taken A, we've done something to the left and to the right of it. We followed that up by something else to the left of it. We just followed that up by a bunch of stuff to the left of it. But somewhere over here in B is matrix A. At this stage, it's got one matrix to the right, one elementary matrix to the right, and a whole bunch of them. We can count them up to the left. Let's call that matrix C. So where we stand now is you got a 1 in that 1, 1 entry, and you got zeros below it. Now let's get zeros to the right of it. So that's what we'll do next. Okay, we'll do that with these elementary matrices that manipulate columns. And it's the same type of manipulation. So we'll take column 2 and eliminate the first entry using row 1. I'm sorry, using column 1. We'll use column 1 to fix things in the third column and so forth. Here's the manipulations. Here's the elementary column operations that we're doing. It's the same thing we just did, except now for columns instead of rows. Okay, so here's where we are now. And this pasted a bunch of more matrices, elementary matrices, to the right of A. So we've got A surrounded to the right and the left by products of bunches of elementary matrices. I can even tell you what they were if you've cornered me on it. So we got a product of a bunch of elementary matrices times matrix A times a product of a bunch of elementary matrices, and we produce this thing. Here's what I mean by this. I sub 1, that'd be the 1 by 1 identity matrix. It's just a 1 entry up here. Below it, we've got a column vector. Let's call it C sub 1. It's 1 wide. It's, what is it, n minus 1 by 1. Over here, we've got 1 by n minus 1. This is just a row vector of zeros of the appropriate size, and this is a column vector of zeros of an appropriate size. We said we were going to do this by induction, so here's the idea. We've got the first row and the first column. We got them the way we want them. We got a 1 here and zeros below and zeros to the right. So what we'll do is move down and over and concentrate on the 2, 2 position. Down and over and concentrate on the 3, 3 position, and keep doing that till we get to the R, R position. And when we get there, we're going to be left with nothing but zeros out there. And that'll be how we draw the conclusion. All right, so this means there's a 1 here, zeros to the right, zeros below, and there's the rest of the matrix. It's been jumbled around. I guess no arithmetic has been done down here yet. But X then is an n-1 by n-1 minor matrix of this particular matrix. Yeah, P1 and Q1, these are products of elementary matrices. All right, how are we doing on rank? We're going to show the rank hasn't changed in all these manipulations. We've got that the rank of A equals the rank of product of elementary matrices times matrix A times product of elementary matrices. That was theorem 3.3.3. So the theory's working for us. If you multiply A on the left and the right by matrices, which are products of elementary matrices, rank doesn't change. I leave it to you to run look that one up. It wasn't that long ago, this section at least. So that doesn't change the rank, and so this new matrix also has rank R. All right, claim that this column space is orthogonal to this column space. All right, remember what this is. This is really a 1 followed by a bunch of zeros. It's just a single column here. Over here, we're looking at what we get from this matrix by eliminating this stuff. This stuff is just a column here in this first stage. Well, you've got all zeros in the first component, and below that, who knows what's going on. But sure, if I take any column vector from here, its first entry is 1 and then all zeros, and I take any column space, I take any column from this matrix over here, first entry 0, and I don't know what happens with the rest of them. But you take an inner product of those two. You take a dot product of one that's got a 1 at the top and all zeros below with one that's got a 0 at the top and who knows below. You're going to get 0 out. So we can say this vector space is orthogonal to this vector space. I bring that up because when you have orthogonal spaces like this coming out of partitions of matrices, theorem 3.3.4 part 4, I guess, tells us that you can add ranks. When you got the orthogonality, you can add ranks. So the rank of matrix A, this parameter R, and this gives us a partition of I guess this matrix P1A Q1, but anyhow the rank is R of that one as well, is the rank of this first part plus the rank of this second part. You know the rank of the first part? Yeah, it's just a column vector. It's a 1 followed by a bunch of zeros. It's a rank of 1. What's the rank of this one? Well, I can figure it out now because we know R equals the sum of the ranks. That's 1 plus this thing. So this thing must have rank R minus 1. So here's where we are. We've proved the claim, or we started to prove the claim, by making the first column and the first row the way they should be, 1s and a bunch of zeros. Now we're going to move over and concentrate on this X sub 1. What's up with it? Its rank is 1 less than what we started with. We'll do the same process. Pull a 1 in the 1, 1 position of this smaller matrix, do all the same stuff, eliminate rows and columns, get in the zeros, and then you'll have a rank, another smaller matrix of rank R minus 2. All right, so if R minus 1 isn't 0, then do it again. Find P2 and Q2 products of elementary matrices where we'll produce something like this. So now we've got the first and the second column. We've got an I sub 2 here. First and second columns are as you want them. First column is a 1 followed by zeros. Second column is a 0, 1 followed by zeros. Remainder of the first and second rows, all zeros. So it's the way it should be. And we get an X sub 2 down here, and the rank's reduced by 1. Again, same argument as above. So keep doing that. Keep doing that until we've got I sub R here, an identity, R by R identity, where R was the rank of the original matrix, zeros here, zeros here. What's happening there? Well, it must be that the X sub R piece must have rank 0. And we could add ranks together. This has rank R here. I know the rank of the whole thing is R, so the rank of this piece here must be 0. This must be all zeros by the summation stuff we had above, for example. So the X sub R must have rank 0. We've subtracted away 1 until I know what's left has rank 0 as well. It's an alternative argument for it. It must be all zeros. So the X sub R is all zeros. And there you go. The original matrix can be multiplied by appropriate elementary matrices on the left and the right to produce this equivalent canonical form. All right, that was a lot of stuff with elementary matrices, but I think y'all would be able to follow that argument because it was it's so mechanical. It's constructive almost. That's how you do row reduction. Okay, we threw in some column reduction. Maybe you don't have experience with that until now, but it's the same ideas. If A were a symmetric matrix, then, you know, the stuff we did to the columns would have been the same kind of stuff we did to the rows. We'd actually write this as P is a product of elementary matrices, and we'd take a P transpose over here and get PA, P transpose would produce the equivalent canonical form of the matrix, provided it was a symmetric matrix. All right, this thing about equivalence, as I said, we're taking equivalence to be a combination of row and column equivalence. We'd say A is equivalent to B if there's a sequence of row operations and column operations that allow you to change A into B. That can also be accomplished by multiplying by elementary matrices on the left and the right. On the left for the row operations, on the right for the column operations. So another way of saying A is equivalent to B in this equivalence sense, not equal, of course, equivalent, is there's elementary matrices, products of elementary matrices, P and Q, such that B equals PAQ. Okay, it seems like it's certainly time, if not past time, to define row echelon form and reduce row echelon form. Here's the symbolic definition. All right, let me scroll down a little bit. Symbols are great, but I really want to know what it means. A matrix R is in row echelon form if the following holds. So we're taking matrix R to have entries R sub I, J. We're saying R sub I, J equals 0 for all I greater than J. So it's further down than it is over in the matrix. So this is saying below the main diagonal, we've got zeros. If K is such that R sub IK is non-zero and R sub IL equals 0 for L less than K, stop there. All right, what does that mean? Means the kth entry in the ith row is the first non-zero entry. It means R sub IK is a pivot in the ith row, so that's their way of saying pivot. Then R sub I plus 1 comma J equals 0 for J less than or equal to K. All right, that means if you go to the next row, you've got zeros below this thing here, below this pivot, and preceding it as well. So the second part means that the pivots go down and to the right, strictly to the right. And that's what row echelon form is. So stated it verbally here. Condition 1 implies that there are only zeros below the main diagonal. Condition 2 implies that R sub IK is the first non-zero entry of row I. It's a pivot. And that the first non-zero entry in the next row lies to the right of that pivot. So the pivots go down and to the right, down and to the right. That's what row echelon form is. Reduced row echelon form, we'd go a little bit further and require that we have zeros above the pivots as well. For any matrix A, there is a matrix P, a product of elementary matrices, such that PA is in row echelon form. Yeah, you can take any matrix and put it in row echelon form using row operations. And row operations are represented by elementary matrices when multiplied on the left. P is a product of those elementary matrices. P is sort of a matrix that encodes the row operations that you did, that took A and reduced it to a row echelon form. I'm not sure it's commented in the notes, but of course the whole problem with this is, if it's a problem, the row echelon form of a matrix isn't unique. As you know, I mean, we didn't require any particular thing about the values of these pivots, these first non-zero entries. We could make them all threes, or we can make them all twos. I mean, it was just zero or not was the only conversation we had in terms of entries when having a row echelon form. So row echelon forms of a matrix are not unique. The pragmatic side of that is, oh, grading this stuff is nightmarish. You have a class put a matrix in row echelon form, they can all get different answers and they can all be correct. The frustrating part in terms of tutoring some of this stuff is you might be helping a student put a matrix in row echelon form. You get one answer, you look in the back of the book, it's got a different answer. Well, you both could be right. That's the problem with row echelon form. Of course, the beauty of reduced row echelon form is there's only one reduced row echelon form. The arithmetic can be a little more lengthy. And fractions might pop up more in reduced row echelon forms than row echelon forms. We'll define that shortly. The proof of this result we just claimed, hey, that's what you do in the Gauss-Jordan elimination. I'm going to defer to my sophomore linear algebra notes on that. I want to define reduced row echelon form. Apparently Gentle doesn't define that, which seems unusual to me. But what we'll simply do is require that each of the pivots be 1 and all the entries above the pivots will be 0. So we'll take row echelon form and add this condition. So matrix R is in reduced row echelon form if it's in row echelon form, and if K is such that R sub I sub K is non-zero and R sub IL equals 0 for L less than or equal to K, stop. Okay, so R sub ik is a pivot, first non-zero entry in row I, is what all those symbols mean. Then R sub ik is 1, okay, we've made the pivots 1, and R sub jk equals 0 for j less than I. J less than I, it's closer to the top than it is to the sides. These are entries above. We're getting entries above R sub ik, and we're requiring those to be 0. Yeah, I want zeros above the pivots, and I want the pivots to be 1. That's what reduced row echelon form is. Another little form, just for the record, while we're talking about forms of matrices, is Hermite form. A square upper triangular matrix H is in Hermite form if H sub I equals 0 or 1. Okay, that means along the diagonal, we've only got zeros and ones. Upper triangular, yeah, I bet you this may not, you get zeros, and under these circumstances, you don't have a full rank matrix. H sub I equals 0, then H sub ij equals 0 for all j. That means that the rows containing a 0 on the diagonal have all entries of zeros. Okay, so you get 0 on the diagonal, the whole row is zeros. H sub I, if H sub I equals 1, then H sub ki equals 0 for k not equal to I. Okay, we're varying the rows. So you're requiring when you get a 1 along the diagonal entry, you've got all zeros above and below it. Implies columns containing 1 on the diagonal, all the other entries are zeros. So in these Hermite matrices, Hermite forms, we're getting lots of zeros. I didn't say you don't have zeros everywhere. Here's a 0 on the diagonal. Well, I don't know, I can have non-zeros above it. It's the row that contains it that has to have zeros. Here's a 1. Okay, then I know I got zeros above and below it. I didn't look at columns. I looked at columns for the zeros along the diagonal and rows for the ones along the diagonal. So there's an elementary little example of where I can get a non-zero entry. Yeah, it's because it's above a diagonal as entry and to the right of a diagonal entry 1. Exercise 3.3.b has you show, here's an interesting feature of Hermite form matrices. H squared equals H, provided it's a square matrix and the product exists. And did we put a condition of square? Yeah, we did talked upper triangular, so we have a condition of square on these. So property of Hermite forms of matrices is you square them and you get the matrix back. H squared equals H. So let's call it quits there with the video. We'll pick up next with a little bit more stuff on rank of matrices. We're going to explore inverses. Well, we'll find out the hard way. I will see you there.